All right, so my last video got cut short a little bit. So that'll occasionally happen. Just to give you an idea of what's going on my end of things, I use my phone to record these videos because that's the equipment that I have. And if I ever get a phone call, it stops my video. And that's what happened. I got a phone call. The video was cut short, so I had to start a new one. But that's what happened. So let's go ahead and move on. We were talking about this theorem here, and the whole point of this theorem was to establish conditions under which a first-order ODE will have a unique solution if it's part of an initial value problem, an IVP. As we saw in the example that preceded this, it is possible for a first-order differential equation or a first-order IVP to have more than one solution, but we want unique solutions. So we're going to see this theorem in action on this last page here. And before we do that, I want to use this graphic to kind of illustrate what was being described there. Because again, if you haven't had Calculus 3, a lot of the terminology and stuff that was used in that theorem might be a little bit difficult to understand. So a couple of the things that we described this rectangle R in the XY plane. And we said that the rectangle R corresponded to the interval AB on the x-axis and CD on the y-axis. So you can see how those two intervals go together to create this rectangle R here. Okay? And then the next thing that we said was that interior to that rectangle is some point x naught, y naught. So that's the point that we're seeing here. Interior meaning it's not on the boundary anywhere, it's inside that rectangle. Okay, having kind of established that setup, we are now thinking about a differential equation of the form dy dx equals f of xy. Okay, and not only the differential equation, but we also have an initial value that comes with it. Y of x naught equals y naught, where the x naught, y naught is that point right there. Okay, what this theorem is saying is that if we focus on this two-variable function right here, f of x, y, if that function is continuous on that entire rectangle R here, and if the partial derivative of this function with respect to y specifically is also continuous on that rectangle, then we're guaranteed a unique solution to this differential equation passing through that point. And as far as the interval of validity goes, for that solution, the interval I naught is some subinterval of this closed interval AB. It has to live within that rectangle, and so it's contained in there somewhere. But not only is it a subinterval, it's also centered at x naught. Remember, we described it as x naught minus h, x naught plus h for some positive value of h. So x naught represents the center of that interval. Okay. In light of this theorem, we have a couple of examples that we want to look at. So first of all, we want to use that theorem to explain why the initial value problem in that previous example was not guaranteed to have a unique solution, which we now know is the case because we checked two different solutions and they both worked. What does the theorem that we just read have to say about that? Well, as a reminder, the differential equation that we were looking at, the IVP, dy dx was equal to x y to the 1/2 power. And we were looking specifically at the point y of 0 equals 0. Okay? Now, let's think for a moment about this guy right here. X y to the 1/2 power is taking the role of that f of xy in the theorem. So I'm actually just going to call it that. F of xy equals x y to the 1/2 power. All right, so what are we looking for? Well, we need to know that the initial condition that we're given here, so this guy right here, y of 0 equals 0, that corresponds to the point 0, 0. Let me plot that in a plane for a second. That's clearly just the origin, right? Now, I want to determine where this function is continuous, because that's one of the conditions that needs to be in place. Well, this function is continuous everywhere that it's defined, but it's only defined for non-negative values of y. Okay, because if y is negative, then we're taking a negative number to the 1/2 power. That gets us into complex numbers, which we're not considering that part of our domain here. So the domain of this function is what we call the upper half plane. Okay, it's all of this stuff up here. Everywhere below the x-axis is where y is negative, and that would be outside of the domain of this function. And this function will be continuous everywhere it's defined, so it's continuous all around here. Now, what does the theorem say? In order for this IVP to have a unique solution, we need to be able to find some rectangle in the xy plane that contains this point. And by contains, it needs to be interior to that rectangle. It cannot be on the boundary of that rectangle. We need to be able to find such a rectangle where not only is this function continuous throughout that rectangle, but so is the partial derivative of this function with respect to y. Well, no matter what, if you look at what the point that we're interested in here, the origin, any rectangle that I can put around that point, such that the point is interior to it, will have to dip below the x-axis at some point, right? It has to dip below somewhere. I can't put the rectangle completely on the x-axis and above it, because then that point would be on the boundary of that rectangle. So again, any rectangle that has that point in its interior is going to venture into territory where the f of x, y here is not continuous. So that means I can't meet the criteria of that theorem, which means I have no guarantee of a unique solution here. Notice I only checked for the continuity of the function f of x, y on some rectangle. I didn't look at the partial derivative of f with respect to y because I didn't need to. I already ruled this out with that first condition. But in a different example, you may find that we can find a rectangle surrounding this point or containing this point in its interior where this is continuous, and then you would have to then go on and check that partial derivative and see if you get the same thing happening there. Okay? Last example that we're going to wrap up section 1.2. So we want to determine a region of the xy plane for which the initial value problem dy dx equals the square root of xy, and our initial value here, our initial condition here is going to be given in a general form, x naught, y naught. We want to find a region in the xy plane for which that has a solution passing through that point within that region. Okay, what do we mean by that? Well, again, I'm missing some terminology. It's not just that we want to have a solution. We want to have a unique solution, because that's what the whole point of that theorem is. We want to have a unique solution. So let's figure this out. Here is the function, or here is the differential equation that we're looking at, which means f of xy is this function right here. F of xy is equal to the square root of xy. Okay, and this time we are going to look at that partial derivative. What is the partial derivative of f with respect to y? Well, again, think of this as a function in which x is being treated as a constant. What would the derivative of this thing be with respect to y? Well, that would be x over 2 times the square root of xy. Okay? I'll let you kind of think through, why that's the case. So, these two functions will be continuous everywhere that they are defined. So really, I'm investigating the domain of these two functions. And rather than thinking of it in terms of intervals, we're thinking of it in terms of regions in the plane, just like the previous example. So let me sketch my x, y axes here. X and y. Starting up here, where is this function defined? Well, we know that because we're looking at a square root of some quantity, we need xy to be non-negative. We need xy to be non-negative, right? Under what conditions is that product non-negative? Well, that's only going to happen if both x and y are non-negative, or if both x and y are non-positive. So what I mean by that, this implies that x and y are both non-negative, or x and y are both simultaneously less than or equal to 0. In that case, their product will come out to a non-negative number. But now let's look at this partial derivative here. What's the domain of this function? Well, because that square root of xy is still showing up in the definition of this guy, we still have these conditions that need to be met in order for a point to be in the domain of this function. But in addition to that, these inequalities allow for this product to equal 0. And that would cause us to divide by 0 here. So we have to exclude that. So here's what we have. X and y now have to be, x and y, or x times y, now have to be strictly greater than 0 so that we're not dividing by 0 up there. That implies the same stuff here with a little bit more of a restriction. X and y are either both positive or x and y are both negative. Neither of them are allowed to equal 0 now. Okay? What does that look like in the plane? Well, x and y are both positive in the first quadrant, and x and y are both negative in the third quadrant. Okay? So if we are going to have a guarantee, according to this theorem, of finding a solution, a unique solution to this differential equation for some point that's given as an initial condition, then that point is going to have to live in either the first quadrant or the third quadrant. So it could be here, for example. That could be x naught, y naught. Because that point is in a position where I can find some rectangle where that point is interior to that rectangle, and everywhere on that rectangle the function f of x, y, and the partial derivative of f with respect to y are continuous throughout that rectangle. That's like the R that we were talking about. X naught, y naught could also live down here, because I can do the same thing. It cannot live on either axis, right? Because then I have the same issue that I ran into up here. All right, so it says, determine a region of the xy plane for which that's true. Well, there's an infinite number of regions we could talk about, because each of these rectangles are a region, right? And I can make this rectangle bigger or smaller as long as it's still completely contained in the first quadrant, and similar down here. So let's be a little bit more general. Any rectangle completely contained in quadrant 1 or quadrant 3. That will work as the region that we're looking for. Any rectangle completely contained in either of those two quadrants. Okay? That's it for section 1.2. It's a shorter section than 1.1, and we have one section left in chapter 1 to talk about.